Welcome to the video lecture on polar coordinates. So far, when we have plotted points on a coordinate system to create a graph, we have used the rectangular or Cartesian coordinate system. The equations whose solutions we have plotted have been in rectangular or parametric form. In this section, we introduce a different way to locate points on a plane. Rather than using a pair of intersecting perpendicular lines, which we call the x and y axis, as reference, instead we're going to use a fixed point called the pole and a fixed ray called the polar axis and refer to points in relationship to these. In the Cartesian coordinate system, the coordinates x, y represent the distance along the x-axis and the distance along the y-axis respectively. In the polar coordinate system, the coordinates r, theta represent the directed distance from the pole to the point and the directed angle counterclockwise from the polar axis to the segment from the pole to the point. So what does all of that mean? Let's see an example of how to plot points in the polar coordinate system. So these 4 points all are called polar coordinates. The first value is r, and the second value is an angle theta. So they're all going to be in the form r, theta. The r is the distance from the pole, what we would normally think of as the origin, out along some ray. And the angle theta tells us what angle that ray should be, starting with a reference point of being this positive x-axis. So in other words, 4, pi over 3 would look like the positive x-axis from here up to pi over 3. So we need to locate where that would be. And if you look at this polar coordinate system right here, let's label some of these angles on here so we can have a reference point. If we look right in the middle, that's going to be your pi over 4 or 45 degrees. This one right here is your pi over 6, and this one right here is our pi over 3. Because if we look at how this is sort of chopped up evenly, we have 1, 2, 3, 4, 5, 6 equal pieces here. So that's like taking this pi over 2 and dividing it into 6 equal pieces, and pi over 2 divided by 6 is pi over 12. So this one right here, even though it's not one of our normal good angles, is actually pi over 12. This would be 2 pi over 12, which is pi over 6. This would be 3 pi over 12, which is pi over 4. This would be 4 pi over 12, which is pi over 3. And that would make this one 5 pi over 12. Let me go ahead and label some of our other good angles. I'm not going to do all of the pi over 12s, but we should know that this one over here is 2 pi over 3. This is 3 pi over 4. And this is 5 pi over 6. That makes this one 7 pi over 6, and this one 11 pi over 6. This one is 5 pi over 4, and this would be 7 pi over 4. And then down here would be 4 pi over 3 and 5 pi over 3. So those are all of our common angles that we would normally see on our unit circle. So now going back to graphing this polar coordinate 4, pi over 3, first you want to locate where pi over 3 would be this ray right here, and we want to go out a distance of 4 along this ray. So 4, if you think of these concentric circles, these are their different radii going out. So 4 would be right here. So think about the circle of radius 4, that would be this one, and this point on the ray pi over 3 has now a distance of 4 on it. So this is our point, 4, pi over 3. Now if we go to 4, negative 2 pi over 3, find your angle first. So normally 2 pi over 3 would be up here in quadrant 2. So negative 2 pi over 3 would start along that positive x-axis and go clockwise. So that would actually be along this ray down here. And we want to go a distance of 4 on it. So again, we're going to go to that circle that has a radius of 4. And we're going to put a dot at where that circle would intersect this ray. So this point right here is 4, negative 2 pi over 3. Now notice the next one. This one is negative 4, comma, negative 5 pi over 4. Let's locate the angle first. Now, positive 5 pi over 4 is down here in quadrant 3. That would be from here going counterclockwise. So if we want to go negative 5 pi over 4, we're going to start at the positive x-axis, but go clockwise, which would put us along this ray right here. So negative 5 pi over 4 is really the same as positive 3 pi over 4. However, our r this time is a negative 4. So how do you plot a negative r? Instead of going out along this ray a distance of 4, what the negative is going to do is it's going to tell us to go in the opposite direction, but along this same ray. So if you imagine drawing this ray, just drawing this line, in other words, that would go through negative 5 pi over 4, by going through that origin, this whole line, normally positive 4 would put us right here, but a negative 4 is going to tell us to go in the opposite direction along this line. So starting from the pole and going in the opposite direction, we would end up over here. So this turns out to be the point negative 4, comma, negative 5 pi over 4. You could also think of it as being the same as positive 4, but along the angle 7 pi over 4. So there's multitude of points that correspond to the same polar coordinate. Okay, let's take a look at our last example, 1 comma 7 pi over 6. So let's find our angle first. 7 pi over 6 is down here. So imagine this ray, and we want to go just a distance of 1 along it. So you have to visualize this circle right here with a radius of 1, and it would intersect that ray right there. So this point is 1 comma 7 pi over 6. So with rectangular coordinates, each x comma y has a unique representation. So every x comma y is exactly one dot on our Cartesian coordinate system. This is not true with polar coordinates. For example, if we plot the point 2 comma pi over 6 and 2 comma 13 pi over 6, let's see what happens. So I'm going to go back to my grid up here. 2 comma pi over 6 would be along this ray right here going at a distance of 2. So it would be right here. Now 13 pi over 6 is 12 pi over 6 plus another pi over 6. And 12 pi over 6 is the same as 2 pi. So in other words, 13 pi over 6 is the same as pi over 6, but it's got one extra revolution in it. But it's still going to end us up along this same ray. So if I'm trying to plot 2 comma 13 pi over 6, it's going to leave me at this same equivalent angle of positive pi over 6, and going at a distance of 2 leaves me right here as well. So this point, this black dot, is the same for both points. So you can have two different polar coordinates that have different coordinates, but they turn out to be the same point on the graph. So let's take a look at 3 comma 5 pi over 6, and let's relabel the point so that it's an equivalent point, but it has a slightly different look to it. For part A, we want the r to be negative, and we want the theta to be positive, greater than or equal to 0. So let's think about what that would have to look like. So imagine 5 pi over 6, that's over here, in quadrant 2, going out a distance of 3. So what would be a corresponding point and give us that same dot, but we would want the r to be negative and the theta to be positive. So if you want to use a negative r, then you're going to need to go in the opposite direction. So what would be this angle going around like this? What's the equivalent pi over 6 angle down here in quadrant 4? It's called 11 pi over 6. So if we used a theta of, say, 11 pi over 6, that would end us up on this ray. But if I let my r be -3, then that would pop me back over to the opposite quadrant, quadrant 2. So in other words, -3, 11 pi over 6 is the same as +3, 5 pi over 6. The angles are opposites, but so are the r's. So that's why they turn out to be the same. Alright, let's try this again using the same point, but this time we want our r to be positive. So it's going to have to stay 3, but we want our angle to be between -2 pi and 0. In other words, we want it to be within one revolution, but we want it to be negative. So what angle could we use that's negative, that's still equivalent to 5 pi over 6? Well, if we want 5 pi over 6, but we want it to be negative, we can just subtract off 2 pi from it to get a corresponding angle. And getting common denominators of 6, 2 pi is the same as 12 pi over 6, and 5 pi minus 12 pi would be -7 pi over 6. So what that means is if I go this direction around, that's the same as -7 pi over 6, and then I would go out a distance of 3 from the origin. So that will end me up at that same point as before. So that works as well. Okay, let's try one last example. This time I want my r to be negative, so I'm going to have to use -3, but I want a negative angle. So we can't quite use this same -7 pi over 6, because that would end us up along this ray, and with a negative r that would flip us over to the opposite quadrant, back to quadrant 4. We don't want that. So what we want to visualize here is what would be a negative angle that's equivalent to this opposite quadrant, so that when we do our -3, that's going to flip us back to quadrant 2. So think about what is a negative angle that's equivalent to 11 pi over 6 over here in quadrant 4. Well, that's the same as going -pi over 6. Again, you could just take 11 pi over 6 and subtract 2 pi from it, and that would give you 11 pi over 6 minus 12 pi over 6, which is -pi over 6. So if we use the angle -pi over 6, that gets us down to this ray, but because the r is negative, it's going to flip us over into the opposite quadrant and leave us off at this same dot again. So that's why it works. We use the negative angle to go down to quadrant 4, but the negative r flips us over to quadrant 2. Okay? So let's take a look at this point, square root of 2, comma, -pi over 4. We want to relabel the point with the same r, and then relabel the point with the opposite r. So in other words, I want two answers here. I want an equivalent point with the same r, so square root of 2, and I want an equivalent point but with a negative r, so negative square root of 2. So let's place where this point is so far. -pi over 4 would be to go down pi over 4. So right here is -pi over 4, and we'd be going out a distance of square root of 2. So this is where we want to end up. So what could we do if we want to keep that square root of 2 being the same? What different angle could we use that's still equivalent to -pi over 4? Well, there's lots of choices, but if you went around going counterclockwise, this angle going around is the same as 7 pi over 4. And you just get that by adding 2 pi. So 7 pi over 4 and -pi over 4 are the same angle, and since we're going the same distance, we're going to end up at the same point. Okay, now let's think about wanting to end up here again, but this time I have an opposite r. So the only way that's going to work is to end up with an angle that's going to put me in the opposite quadrant, so that when I go around this way, for example, to that angle, then the negative r will flip me over here into quadrant 4. So what's the corresponding pi over 4 angle that lands us in quadrant 2? Well, this is called 3 pi over 4. So if I go to 3 pi over 4 first, but then the negative r flips me over into the opposite quadrant, then I'm going to end up right here where I want to be. So this works, and this works. Now, to convert coordinates between the rectangular system and the polar system, we're going to superimpose the two systems on top of each other and observe the relationships. So let's imagine drawing a ray out here. This is my distance r, and this is my angle theta. And what I'm going to do is I'm going to drop a perpendicular down, and this point would either be called r comma theta in the polar system, or in the Cartesian or rectangular system it would be called x comma y. And in the Cartesian or rectangular system, the x would be this horizontal distance, and the y would be this vertical distance. So what's the relationship between x, y, r, and theta? Well, by Pythagorean theorem, we know that x squared plus y squared has to equal r squared. And that's just based on the fact that this is a right triangle. So that's one relationship that we know. We know by trigonometry and right triangle definitions of our trig functions that the sine of theta should be the opposite side, which is our y, over our hypotenuse, which is r. And we know that cosine of theta should be the adjacent side, which is our x, over our hypotenuse, which is r. And we know that tangent of theta should be opposite over adjacent, so that would be y over x. So tangent of theta is defined to be y over x, and we can use these other two relationships here and here to solve for y and x. If I multiply this equation by r on both sides, these cancel out, and I just get y is r sine theta. And if I multiply both sides by r here, these cancel out, giving me x equals r cosine theta. So here's the relationship. To get x, you would take your r times cosine of theta. To get y, you would take your r times sine of theta. And if you want to find out what your polar coordinates are using x's and y's, to get your r, you would use that r squared is x squared plus y squared, and to get your angle theta, you would use tangent of theta is equal to y over x. So what we're going to do next is convert back and forth between our two different systems. So let's start with polar coordinates and convert these to Cartesian coordinates. So here we're given the r and the theta, and we want to turn them into x's and y's. And the basic formula for that is what we just talked about. X is always going to be r times cosine of theta, and y is going to be r times sine of theta. So this is slightly easier to do than the other direction, which is what we'll do next. So to figure out x, we're going to take our r, which in this problem is this -2, times the cosine of our theta, which in this problem is minus pi over 2. Well, cosine of pi over 2 or minus pi over 2, that's 0. And -2 times 0 is going to stay 0. To get y, we're going to take our r, which is that -2, times the sine of minus pi over 2. And remember, minus pi over 2 is the same as 3 pi over 2. It's down on the negative y-axis, so this goes to -1. So -2 times -1 means y is going to be +2. So this point is the same as 0 for x, 2 for y. Now let's try the next one. So now my r is -1 and my theta is pi over 4. So x should be the r times the cosine of the theta. Cosine of pi over 4 is √2 over 2 times that negative is just going to make it negative. So x is minus √2 over 2. What's y? Well, to get y, we're going to do that same r times the sine of pi over 4, which is also √2 over 2, times that -1 makes it negative as well. So y is minus √2 over 2 also. And then for the last example, my r is 2 and my theta is -7 pi over 6. So x is going to be the r, which is 2, times the cosine of minus 7 pi over 6. And on a unit circle, just so that you remember, 7 pi over 6 is normally over here in quadrant 3. So we want to go that same distance but going clockwise, this way around. So 7 pi over 6 is going to be right here. Because this would be negative pi over 6, negative 5 pi over 6, negative 7 pi over 6. So it's a pi over 6 angle, which means that the cosine is a root 3 over 2, but since it landed us in quadrant 2, cosine is negative in quadrant 2. So we're going to get a negative root 3 over 2 times the 2 out front. The 2's cancel, so that means x is minus root 3. Now let's do y. Y is going to be the r, which is our 2, times sine of negative 7 pi over 6. Sine of every pi over 6 angle is always a 1/2, and in quadrant 2, sine is positive. So this is a positive 1/2 times that 2. The 2's cancel, giving us just 1. So y is 1. Okay, so in these 3 examples, we started with polar coordinates, and we plugged into these 2 formulas here to find our Cartesian coordinates. Now we're going to go in the opposite direction. So we're going to be given x's and y's, and we're going to try and figure out what our r's and thetas are. And this particular problem asks us to use positive r's and thetas between 0 and 2 pi. So this is my x, and this is my y. Now to figure out your polar coordinates, instead of using x equals r cosine theta and y equals r sine theta, this time we're going to use the formula that x squared plus y squared is equal to r squared, or in other words, r itself would be the square root of x squared plus y squared. So let's find our r first. R is going to be that hypotenuse of that triangle. So we square the x and we square the y. That's going to give me 9 plus 9, or 18. And if we simplify that, that's equal to a square root of a 9 times the square root of a 2, which turns into a 3 root 2. So my r is 3 root 2, and I'm using the positive square root there since they asked us to use a positive r. Now to get your theta, we're going to use the fact that tangent of theta is opposite over adjacent, and on our right triangle that was the y over the x. And we're just using that little right triangle where this was the r, this was the x, this was the y, and this was theta. So if we want to find theta, we're going to set it up so that tangent of theta is equal to whatever our y is, so negative 3, over whatever our x is, which is 3, and that reduces to a negative 1. So what kind of angles have tangent of theta equaling negative 1? And what quadrant are we in? Think about what quadrant this would have to be in. If x is positive and y is negative, this is a quadrant 4 point. So we want an angle that's in quadrant 4 where the tangent is equal to a negative 1. Well, tangents are equal to 1s at pi over 4 type angles. So what's the name of the pi over 4 angle that is in quadrant 4? Well, that's equal to 7 pi over 4. So this theta is 7 pi over 4. That's the quadrant 4 angle that we would need to have tangent of theta be negative 1. Okay, let's try this one more time. So this time our x is negative 1 and our y is square root of 3. What quadrant is that in? Well, if x is negative but y is positive, that's a quadrant 2 angle. So whatever theta we come up with, we want to make sure it lands us in quadrant 2. Let's find our r first. To get your r, you're just finding that hypotenuse by taking the square root of the x squared plus the y squared. Well, square root of negative 1 is positive 1. Square root of 3 squared is just 3. And that gives me square root of 4, or just 2. So my r is 2. And then to get my theta, I'm going to set it up so that I want the tangent of theta to be my y, which is this root 3, over this x, which is this negative 1. So this is going to reduce to a negative root 3. So what angle is going to give me that? Well, think about this for a moment. The way that this comes about is it's really like taking a sine over a cosine, where the sine is this root 3 over 2 and the cosine is this 1 over 2. What kind of angles have the sine being square root of 3 over 2's and the cosines being 1/2? Well, those are pi over 3 angles, and you can look at your unit circle to remember that. So this is a pi over 3 type of angle. But what's the name of the pi over 3 angle that lands us in quadrant 2? It's 2 pi over 3. So theta has to be the 2 pi over 3 angle. So now we know r, and now we know theta. Okay? So make sure you know how to convert back and forth between polar coordinates and Cartesian coordinates. The next thing that we're going to do is convert back and forth between polar equations and Cartesian equations. So in these next examples, these are all examples of what we would call Cartesian equations because they involve equations involving x's and y's. And what we want to do is change them so that they turn into polar equations. So you should only see r's and thetas involved instead of x's and y's. And the way that you're going to convert these into polar equations is to use those relationships that x is equal to r cosine theta and y is equal to r sine theta. So if I see y equals to 2, what I'm going to do is replace this y with what it's equivalent to in polar form, which is r sine theta. So I'm going to substitute in r sine theta for this y. Now this particular problem, and this is usually how it's asking it, is it's asking us to express our answer as r equals a function of theta. In other words, we want to get r by itself on one side, and we want to get all the thetas on the other side. So how would I go about solving this for theta? Solving this for r? I would have to move this theta over to the other side, and it's a sine theta. So to do that, I can just divide both sides by sine of theta. That'll cancel these out, giving me this r by itself. And you could leave it like this fraction, but I prefer to clean it up a little bit. Sine of theta in the denominator, that means it's like a reciprocal of sine. What function is the reciprocal of sine? Cosecant. So we could change this 1 over sine theta into a cosecant of theta and just leave that 2 on top. So here is my answer. R equals 2 cosecant theta is exactly the same equation as just y equals to 2. Let's try it again. So this time we have x squared equals to 8y. So the first thing I'm going to do is replace this x with what it's equivalent to, and it's equivalent to an r cosine theta. And I want that x squared, so I need to square all of that. Then I'm going to replace this y with what it's equal to, which is r sine theta. And now I need to try and manipulate this a little bit. So first let me go ahead and square my r and square my cosine. And I'm going to get rid of the parentheses on the right-hand side. Now on this particular example, one thing we can do to try to simplify it is we can divide both sides by r. And you can only do that if you know that r can't be 0. And we know that r can't be 0 because if r was 0, then we would have a graph that's just right at the pole, or the origin. And this graph right here is obviously not just the point 0, 0. So it's okay in this problem for us to divide by 0 because we know that r can't just be 0. So if I divide by r, the reason why that helps is it gets me just an r on the left, cosine squared theta, and I lose that r on the right. So now all I have to do to finish solving this for r is divide by the stuff that's next to it. So I'm going to divide both sides by cosine squared theta. Now, again, this is kind of up to you how much simplifying you want to do here, but I'm going to show you one way that we could simplify this. Let me break up this cosine squared into a cosine theta times a cosine theta. And I'm going to put this second cosine theta underneath a 1, just so you can see how we're really going to transform this. This part here, sine theta over cosine theta, is a tangent. So this could become 8 times tangent of theta, and 1 over cosine theta becomes a secant. So our final answer is r equals 8 tangent theta secant theta. And that, to me, just looks a little bit cleaner. Okay, let's take a look at this next one. So here we're going to replace this this y with what it's equivalent to, which is r sine theta. And we're going to replace this x with what it's equivalent to, which is r cosine theta. And again, we're going to pull the same trick that we did in the last problem, in that we know that r can't just be 0, because if r is 0 on a polar graph, all you're getting is the pole. Okay, if r is 0, that's just the origin. And we don't have the origin as this graph. We know that this is supposed to look like a line. Y equals 6x is just a line, it's not just a dot. So we can divide both sides by r to help clean this up a little bit. So we're left with sine of theta equals 6 cosine theta. Now this problem is a little bit strange in that it doesn't have an r left. After we divide through by that r, it's gone. So what does that mean we're going to do? If we're trying to solve this for r, we can't, because there is no r left to solve for. So instead of solving for r, what would make some sense here would be to solve for theta. So that's what I'm going to do instead, since we lost our r. Now to get our thetas together, what I'm going to do is divide both sides by this cosine of theta. You could have also divided by sine, but I'm going to try to get this right-hand side to just become a 6, and sine over cosine we know becomes a tangent. Now what could I do to finish solving this for theta? Well, I'd have to undo the tangent. And what function undoes a tangent? That's an inverse tangent. So I'm going to take an inverse tangent of both sides. That's going to cancel out this tangent over here and leave me with an inverse tangent of 6 on the right side. Now think about why that would be the same as this graph right here. Y equals 6x is just a line that has a y-intercept of 0 because there's no b, and the slope is this 6, so it's a fairly steep line like that. Why would this be the same thing? Well, think about what it means. Inverse tangent of 6 is just some angle. We would have to use our calculator to actually figure out how many degrees or how many radians this actually is. But it's just an angle. So this is saying graph on your polar grid every point that has an angle that's equivalent to inverse tangent of 6, and since there's no r can be anything. So this angle right here turns out to be the inverse tangent of 6, and if you let r be anything positive, that gives you all these points, and if you let r be anything negative, that gives you all these points. So by letting r vary and be any real number, but restricting the angle to be this particular angle right here, you do generate that whole line. So that's why these two equations really do graph you the same exact picture. Okay, so on all three of these, we took a Cartesian equation and we converted it to polar form. Now what we're going to do is start with a polar equation and turn it into its Cartesian form. So to do that, you are going to again be using some of these relationships. X equals r cosine theta, y equals r sine theta. We also might need that relationship that x squared plus y squared equals r squared, or tangent of theta is equal to y over x. So we might be using any of these. So let's start with r. On this first one here, if r is just equal to 3, what could we do to find out what this is in its Cartesian form? Well, we're going to use this formula right here, because this is the one that utilizes r in terms of x's and y's. Now what would r be if we solved this for r? It would be the square root of x squared plus y squared. So I'm going to substitute in for this r the square root of x squared plus y squared, and I'm going to set that equal to that 3. Now let's clean this up a little bit. If I wanted to get rid of that square root, I would square both sides. And that gives me x squared plus y squared on the left, and it gives me 3 squared or 9 on the right. What does the graph of x squared plus y squared equal to 9 look like? It's just a circle. It's a circle with its center at the origin and a radius of 3 all the way around. So the graph of this equation right here is this. And that should correspond to what our interpretation of r equals 3 means, because there's no angle here. So we're allowed to let theta vary all the way around this circle as long as the radius, that r, is always 3. So this is also a circle as well. So that's why these match. And we can't really solve this very well for y because it's not a function. You can, but it's not necessary. I would just leave your final answer in this x squared plus y squared form. Okay, let's take a look at theta equals to pi over 4. How could we figure out what that's going to be? Well, think about what the graph of that would look like. If theta is supposed to be pi over 4, here's pi over 4. What's r in this equation? Since there isn't one, r can be anything. So if r is anything positive, it's going to give us all of these points going up and to the right. But if r is anything negative, that's going to swap us over down to quadrant 3 and give us any of these points going down and to the left. So theta equals to pi over 4 is this line. So what we would expect to see for our answer here is an equation of a line. So how could we come up with it? Well, if I want to figure out what this is in terms of x's and y's, and all I have here is a theta, I'm going to use this relationship right here. If I solve this for theta, we would need to take an inverse tangent of both sides. So in other words, theta would just be the inverse tangent of whatever y over x is. So I'm going to substitute in for theta inverse tangent of y over x. And now what I'm going to do is I'm going to undo this inverse tangent. Well, what undoes an inverse tangent? A tangent. So if we take the tangent of both sides, we're doing it to both sides, so we're keeping it equal, these will cancel each other out, just giving me y over x. And what's the tangent of pi over 4? It's just 1. And then if I multiply this x on both sides, these cancel out, giving me just y, and 1 times x is x. So that is exactly this line right here that has a slope of 1, and it goes through the origin. So these are both lines. And they're the same. Okay? Let's try another one. R sine theta equals to -2. We want to put this into Cartesian form. So we want to get rid of all the r's and all the thetas. Now you could take r and substitute in the square root of x squared plus y squared and then try to do something fancy with this sine of theta. Instead, the trick here is to recognize that we know what r sine theta is. It's just y. So this whole quantity here just becomes y. And that means our Cartesian equation is just a horizontal line at a height of -2. So that's what the graph would look like if we needed to graph it. Okay, how about r squared sine 2 theta equals to 4? Now, in order to do this, you have to be a little bit clever here. First thing you should probably notice is that we don't just have a theta, we have a 2 theta. So I would recommend remembering some of your identities. What is another way of thinking of sine of 2 theta? Using that double angle identity, this is the same as 2 sine theta cosine theta. So I'm going to substitute that in right here. And I'm going to pull that 2 all the way out, and this becomes 2r squared sine theta cosine theta equals to 4. Now we're going to be clever like we were in the last problem. Remember that x is defined to be r cosine theta and y is defined to be r sine theta. So if I see an r times sine theta in this equation, I'm going to replace it with a y. And if I see an r cosine theta, I'm going to replace it with an x. And one way that we could do that, and again, this is just being a little bit clever, you probably wouldn't think to do it the first time you see this problem, so it takes some experience. But what we're going to do is we're going to break up this r squared. I'm going to put one of the r's in front of the sine theta and the other r in front of the cosine theta. So if you were to multiply this all together, you get back what we started with. I'm just splitting up that r squared so that this r sine theta becomes our y, and this r cosine theta becomes our x, and we still have that 2 out front. If I divide both sides by 2 to try to clean this up a little bit, I get y times x is equal to 2, and if you really wanted to solve for y, you could divide both sides by x and get y equals 2 over x. So this is a rational function. Okay, so this equation right here is the same as this Cartesian equation. So that one was a little bit tricky. The last one here also is going to be a little bit tricky. Again, you probably won't think to do this if you've never done a problem like this before, but after you've seen one or two of them, you want to remember this trick of what we're going to do. So here's the idea. On the last two problems, we were able to be a little bit lucky because we had an r sine theta in the problem. I had it here and I had it here, and I turned both of those into my y's using this formula. On the right hand side of this problem, I have the sine theta, but I don't have the r, which makes this really hard to just substitute in a y. So here's what we're going to do. We're going to get that r that we're missing on the right hand side by multiplying both sides of this equation by r. And as long as we do it to both sides, we're keeping it balanced. Now on the left side, r times r becomes an r squared. And on the right side, I'm going to squeeze that r in between here, so this would become negative 2r sine theta. So this now can be replaced by y, and my right side becomes negative 2y. Now what can I do with that r squared? Well, remember up here what r squared is? R squared is just x squared plus y squared, and it comes from that hypotenuse in that Pythagorean theorem. So I'm going to replace this r squared with x squared plus y squared. Now I'm going to get a 0 and move this 2y over to the left side so it becomes positive. And hopefully you've done enough of these problems in the past that when you look at this equation, you should be able to tell what it is. It's a circle. And the reason I know it's a circle is because I have an x squared and a y squared. They're being added, and the coefficients of the x squared and the y squared terms are both 1. However, it's not in what we would normally consider our standard form for a circle. There's no other x terms, so that x squared is fine, but the y's do have a couple of different y terms here. So what we're going to do is we're going to complete the square on these two y terms. So what I'm going to do is I'm going to try to factor this. Y plus what quantity squared would FOIL out and give me back a y squared plus a 2y? Well, what I would have to have in the parentheses right here would have to be half of this middle coefficient, and half of 2 is 1. So if I were to FOIL this out, I am going to get that y squared back. I'm going to get a y plus a y, which is that 2y, but I'm also going to get a plus 1 on the end when I FOIL this out, and there is no plus 1 in this original problem. So what we do to complete the square is we add in that 1, but we balance it out by adding it to the other side as well. So now these three terms do factor into this quantity squared, but now on the right side I have a 1. So here's my final equation. It's x squared plus y plus 1 squared equals to 1, and that's just a circle with center for x being 0 since there was nothing being subtracted or added to that x, And the center coordinate for the y would be the opposite of this number in the parentheses, so a -1. And what's the radius of our circle? It's the square root of the constant on the right side, and square root of 1 just stays 1. So this is just a circle with the center at -1 on the y-axis and a radius of 1. So it's going to have a graph like that. Now we've been doing a lot of graphing, so that's what we're going to finish up with today, is how to graph some of these polar functions. And to do that, you can convert to their Cartesian equation first if you prefer, but sometimes that can be difficult to do, and it takes a little bit of time. So what I'm going to show you on this next page of notes is basically a summary of some of the most common types of polar graphs that you're going to see. And if you're a memorizer like I am, then you just kind of want to memorize some of the trends that we're going to see in this chart and use that to help you get your graphs of your polar functions pretty quickly. So the first kinds of common polar graphs that you are going to see are things of this form over here, where you have r on the left, and then you have some number a that's either plus or minus some number b times either cosine theta or sine theta. And these are called lemmasons. And there's different kinds of lemmasons based on the size of a and the size of b. So these first four right here all fall into a similar category called a lemmason with an inner loop. And this will happen if your a constant, the one that's out front, divided by your b is less than 1. In other words, if the a number is smaller than your b number. Now if it's a cosine function that is in your equation, then this is going to be a lemmason that either points to the right or to the left. If it's a plus cosine, then it's going to be a lemmason that points to the right. And if it's a minus cosine, it's going to be a lemmason that points to the left. And these have an inner loop when that a divided by b is less than 1. So this is kind of what it looks like. Whoops, let me try drawing that a little bit better. See if I can do it a little bit more clearly with my pen. So it's kind of like this heart shape pointing to the right, but there's this little inner loop inside. And it's pointing to the right because this is a plus and it's a cosine. For the minus cosine case, it looks just like this, but it points to the left. So again, it looks kind of like a heart shape pointing to the left, but then you get this little loop on the inside. For the sines, these are going to point either up or down instead of left or right. If it's a plus sign, then you're going to get this heart shape pointing up with that little inner loop. And if it's a minus sign, it's going to be this heart shape pointing down with this little inner loop. So those are your lemmasons with an inner loop. Now in these four right here, notice the A and the B are the same. So you have A. So these are called cardioids, and they're just a certain type of lemmason. And this is when that A over that B is equal to 1. In other words, the A and the B are equal. And you see that in these equations. So AA and so forth. So this time it's going to look just like a heart, but with no inner loop. So if it's a positive cosine, it's going to be that heart shape pointing to the right and there's no inner loop. If it's a minus cosine, it's this heart shape pointing to the left with no inner loop. If it's a plus sign, it's this heart shape pointing up. And if it's a minus sign, it's this heart shape pointing down. For the next four, down here, these are going to be called dimpled, kind of like dimples, dimpled lemmason. And these occur when your A over B is bigger than 1 but less than 2. So something between 1 and 2. So the A is a little bit bigger than the B, but not so big that you're outside of this region. So this is what it would look like. it's still going to be sort of that heart shape, but it doesn't go all the way to the pole. It looks something kind of like this. There's this little dimple on the negative x-axis, and then it has that heart shape. So for the minus cosine, you would get this little dimple on the positive x-axis, and then it loops back around. So it's kind of a heart shape, but it doesn't go all the way down to the origin. It just kind of puckers in a little bit on the negative or the positive x-axis. For the a plus b sine theta, it's going to look similar, just a little dimple right there on the negative y-axis, or a little dimple on the positive y-axis. And then for the last four here that are also lemmasons, this is called a convex lemmason, and this occurs when your a divided by your b is greater than or equal to 2. So these are going to look even more exaggerated than these, and it's kind of hard for me to graph these or show these very clearly on here, but it's still sort of that heart shape, but it almost looks kind of flat or vertical right where that dimple wants to be, and then it comes around like this. And then for the minus cosine shape, it's again slightly vertical right where that dimple wants to be, and then it's that sort of heart shape. So it's hard for me to show you that very clearly with my pen, but you can see some examples drawn in your textbook that would show you this a little bit more clearly. So for the sines, it's going to be this little flat horizontal piece, and then it goes up and around. And then for the minus b sine theta, it's a little flat horizontal piece, and then it goes down and around. So something kind of like that. And I'm going to show you when we do examples of how to actually plot points, so you can get a good feel of which shape these are going to have. Now we're going to look at a few other types of graphs. So you'll see lemmasons quite often, but you're also going to see what we call rose curves quite often. And these are similar in that they all have equations that are r equals a number a times either cosine n theta or sine n theta. So here's something that's important to know. If the n is odd, you're going to have exactly n petals on your rose. However, if the n is even, then you have 2 times n, or twice as many petals as you would normally have. Okay, so this is what it's going to look like. For the cosine cases, these are symmetric over the x-axis. So you want to make sure that you see that symmetry over the x-axis. If the n is odd, then you're going to have exactly that many petals. And I'm going to draw here. I can't really draw all of them, but I'll show you what the case might look like if n is equal to 3, an odd number equal to 3. So this is what it looks like. For cosine, your first petal is always centered on the positive x-axis, always. And then, since there's 3 petals, we want them evenly spaced around this whole graph. So the other petal is going to be over here, and the other petal is going to be over here. These should all be evenly spaced apart. And the length of this petal, so this sort of distance going out to the tip of that petal, that's your A. So this is A, and this is A. Now if the n is even, like if I drew n equals to 4, your first petal is still going to be on that positive x-axis, but then you're going to have twice as many petals. So for the odd case, this only had 3 petals, but for n equal to 4, this is going to actually have 8 petals. So we need to evenly space out 8 petals. So 4 of them would be on your 4 axes, and then the other 4 are going to be in between those. So it looks just like a flower where each of these has a distance of A going out to that petal length. So that would be what it would look like if n was 4. So it's going to be similar for the sines, but this time instead of being symmetric over the x-axis, and you can see that over here, if I were to flip these over that x-axis, you would just get that reflected image right back. For sine, instead of being symmetric over the x, it's symmetric over the y. So if n is odd, like n equals to 3, we're still just going to have 3 petals, but your first petal, instead of being on the positive x-axis, it's on the positive y-axis. So this would look evenly spaced out like that. And this distance here would be that a. Okay, if we look at r equals a sine n theta for n being even, let's take an example like n equals 2, for example, then that would have to have 4 petals. And that is going to have the first petal not being on the y-axis, but it's actually going to have to be over here in quadrant 1 to maintain this symmetry over the y-axis. So then the next petal would be over here symmetric to that, and then you'd have your other 2 evenly spaced over here, where this distance is your a. So it looks a little bit different in that it's not consistently always centered on that y-axis. It depends on how many petals there are. Okay? The last kind of graphs that we're going to look at are circles and lemniscates. So circles look just like your roses, except there's no n next to that theta. So your circle would be r equals just a cosine theta or a sine theta. So there's no n in front of that. So it's like having a rose but with only 1 leaf because your n is 1. So that makes it kind of easy to see what this would look like. If you want a cosine theta, it's like having a rose with only 1 leaf centered on that positive x-axis, so you get a circle that looks like this, where that diameter is a. So this is just a circle, and then for a sine theta, it's going to be a circle centered on the y-axis, where this diameter is a. So these would be your 2 circles, and then the last 2 look very different because they have r squared on the left side, and then an a squared, and either sine 2 theta or cosine 2 theta. These are called lemniscates, and they look kind of like maybe an infinity symbol, if you want to think of it that way. The sine one is angled like this, kind of like a figure 8. So the cosine one is like an infinity symbol on its side, like that. So this distance here is your a, and this distance here is your a. Okay? So let's practice graphing these. Here's a couple of strategies to think about. The first thing I would recommend is recognizing those basic forms. So is it a lemmason or a cardioid? Is it a rose? Is it a circle? Or is it a lemniscate? If you want to consider symmetry, you can use that to help you out. And then we're definitely going to probably want to plot points. And if all of that fails, or if it's none of these nice forms, you can always convert your equation into its Cartesian form and graph it that way instead. So let's try some out. So here's our first example. R equals 3 minus 3 cosine theta. So this is one of those lemmasons, but the A here and the B here are the same. So this is actually going to be a cardioid. And because it's a cosine, that's minus, it's going to point to the left. So that's always nice to have in your back of your head. We know that this is going to look like that heart shape pointing to the left like that. Now to get some exact points, you're definitely going to want to plot some r's and some thetas. We're not using x's and y's here, we're using r's and thetas. I always like to do my thetas first and plug those in and then figure out based on that what the corresponding r is. And when you're picking your thetas, you always want to pick nice values, things from your unit circle, and just kind of think of some of those key points, enough points to kind of get the shape down. So I always start with theta being 0, and then maybe I'll look at pi over 2, and maybe I'll look at pi, and we'll go from there. Maybe we'll have enough information once we graph these 3 points. So let's plug them in to our equation. If I let cosine be 0 right here, cosine of 0 goes to 1. And 3 minus 3 times 1 is just 0. So when theta is 0, r is 0. Now let's let theta be pi over 2. So if I put a pi over 2 here, what's the cosine of pi over 2? Well, cosine of 90 degrees is 0. So this whole second term goes to 0. 3 minus 0 means this is going to be 3. Now if I let cosine be pi, or excuse me, if I let theta be pi, cosine of pi is negative 1, because that's 180 degrees. So we get 3 minus 3 times negative 1, which is 3 plus 3, or 6. So this goes to 6. Let's plot a few more points here. Let's look at 3 pi over 2 and 2 pi as well. We'll just go all the way around our circle. So now if I let this theta be 3 pi over 2, cosine of 3 pi over 2, that's back to 0. So we get 3 minus 0 is 3. And if I let theta be 2 pi, cosine of 2 pi is back to 1. 3 minus 3 times 1 is going to be 0. So we've got a few points here to plot. Now remember, we're going to start with our angle. If theta is 0, then that's going to just be right here on that positive x-axis. And my r is 0, so we're not going out any distance along that x-axis. So 0 for theta and 0 for r is just the origin, just that pole. Now if I go to pi over 2, that's 90 degrees up here. So we're supposed to be along this ray, and we want to go out along it a distance of 3, which would be right here. So we go from this point to that point. Then at pi, an angle of pi is over here along this ray, and we want to go out a distance of 6. So we're going out along this ray a distance of 6. So we would be here. 3 pi over 2 is down here, and we want to go out along it a distance of 3, so to here. And then at 2 pi, which would be back to the positive x-axis, we're going out a distance of 0, so we're back to the origin. Now that's only 4 points, and they're nice and lined up, but if you remember that this is that cardioid shape, then you know kind of how you should be connecting them. This is going to come along here like this and go like that. And if you wanted more points, you certainly could plot pi over 3s, pi over 4s, pi over 6s to get some of these arcing points over here. And you can plot any more additional points that you want. But if you already know that this is supposed to be heart-shaped, then it's pretty easy to figure out what it should look like, as long as you kind of get those 4 basic corner points in place. Let's try another one. R equals 1 plus 2 cosine theta. So this is one of those lemmasons again. The a here is 1 and the b is 2. So if I do a divided by b, that's 1/2. That's less than 1. So this is going to be one of those lemmasons with an inner loop. And because it's a positive cosine, that means it's going to point to the right, and it comes into the origin, and it's that heart shape, but then it has this little inner loop inside. So that's kind of what we're expecting to see in our graph. So I'm going to make a little table again of thetas and r's, and I'm going to kind of provide a few more points here because I want to make sure that I see that inner loop and where it's going to go. So let's think about what would be some thetas that might be useful to do. Obviously 0, and then if we kind of go in order here and look at our equation a little bit, we normally would probably use pi over 2, but is there anything else that we might use before or between 0 and pi over 2? Any of these angles over here that might be useful to us? And remember, cosine takes on the value of 1/2, which would cancel that 2 out front very nicely. What's the angle that makes cosine turn into a half? Pi over 3. So that might be a good point to consider when you're making your table. Okay? In addition, we can do some more points. We could look at our pi. We could look at our 3 pi over 2. We could look at some of those other pi over 3's, like 2 pi over 3 or 4 pi over 3, and you can plot as many points as you find necessary until you get a good feel for how this graph is going to look. And they don't necessarily have to go in order like mine don't, but it's kind of nice to try to keep them in order so it follows easily on your graph. So let's go ahead and figure out what some of these r's are going to be. Let's let theta be 0, so this goes to 0. Cosine of 0 is 1, so we get 1 plus 2, which is 3. Now let's let theta be pi over 3. So this goes to pi over 3. Remember we said cosine of pi over 3 is a half, and when I multiply that by 2, that cancels out to a 1 plus the 1 that was out front, so this is going to be 2. Now let's let theta be pi over 2. That means cosine of pi over 2 goes to 0. 1 plus 0 is going to be 1. Let's look at cosine of pi. Cosine of pi is negative 1 times that 2 makes it negative 2, plus the 1 out front makes this negative 1. Now let's look at 3 pi over 2. I like to look at all 4 of our major quadrant angles, so 0, pi over 2, pi, and 3 pi over 2 are always good to look at. 3 pi over 2, the cosine of that is 0 again, so 1 plus 0 is going to make this be 1. And then let's look at a couple more of those pi over 3 angles. If this is 2 pi over 3, cosine of 2 pi over 3 is going to be a 1/2, but it's going to be negative because that's a quadrant 2 angle. So when I multiply that by 2, these cancel out and give me a negative 1 plus the 1 out front, so this is 0. If I look at 4 pi over 3, that's also a 1/2, but it's also negative because it's a quadrant 3 angle. So when I multiply by 2, that gives me that negative 1 again, plus 1, so this is also 0. And if you wanted that last pi over 3 angle, which was 5 pi over 3, the quadrant 4 version of the pi over 3 angle, then quadrant 4 cosine is positive, so this is positive 1/2 times 2, which is 1, plus 1, so this is back to 2 again. So let's plot our points. If theta is 0, we're out here along the positive x-axis, and we want to go out a distance of 3. So that would be right here. At pi over 3, which is up here, we want to go out a distance of 2. At pi over 2, we want to go out a distance of 1. At pi, we want to go out a distance of negative 1. So be careful here. Pi would tend to make us go this way if the r was positive. But if the r is negative, like this one is, then we flip over and we go in this direction 1. So that's actually going to be right here. At 3 pi over 2, which would be down here, we go out a distance of 1. At 2 pi over 3, which is this ray right here, we go to 0, so that's going to be right at the origin. At 4 pi over 3, which is this ray, we're also going out 0, so back to the origin again. And at 5 pi over 3, which is over here, we go out a distance of 2. So we want to kind of put all these together and make it look like this lemmason with an inner loop. So you're going to have this heart shape. And I need to make this a little bit wider. So it's going to come out here, because we've got to hit those 2's, and then we have this little inner loop on the inside. So it's going to look just like that. Now let me show you how you can graph this on your calculator as well. Just so you can double check your solutions. You will need to be able to graph these by hand, but you can graph them on your calculator. But in order to do that, you need to change your mode. So go ahead and click Mode, and the normal default is to be in function mode, and that's what we would use if we were graphing Cartesian equations. So what I want to do is change this by arrowing over to polar and press Enter. And so now we're going to be in polar form. and I'm going to go to y equals, and instead of being y equals, now these are all going to be r equals because we're in polar form. So we're just going to type in this equation, 1 plus 2 cosine theta. And I guess I should say one word of warning here. When you're in that mode again, make sure you're also in radians. You always want to be graphing sines and cosines using radians. And mine already is, but just double check that yours is in radians and not degrees. So here's my r equals, and I'm going to do a zoom standard here, just like we normally would, and we'll see our graph. And it's kind of tiny because we're a little bit too large going up and down and left and right. So let's hit window. And here's what it's going to look like. It's a little bit different looking this time because you now have parameters for theta as well. So theta min here is 0, and this would be 0 radians. Theta max is set at 6.28, which is actually 2 pi. And theta step is about pi over 24 or something like that. And you can adjust that to be whatever you want. But I'm just going to leave the thetas the way they are because this is going to allow theta to sweep through 0 to 2 pi. What I'm interested in changing are the x-mins and the y-mins and the x-maxes and y-maxes because that graph was too big. So let's let our x-min say be -5 and our x-max be 5, and let's let our y-min be -5 and our y-max, keep arrowing down and you'll see that y-max show up, be 5. And now let's hit graph, and there it's a little bit more clear. So there's our lemmason with our inner loop, and I kind of made mine a little bit too pointy over here in my example, but it's almost kind of looks circular a little bit with this little tiny inner loop inside. Okay? Alright, let's take a look at another example.
Okay, if we take a look at our next example, we have r equals 4 plus 3 sine theta. And if you refer back to your sheet of all the different kinds of graphs we have, this is a lemmason. And what we want to focus on a little bit more closely before we graph this is what kind of lemmason it is. So we need to look at these coefficients. The a is this constant out front, which would be 4, and the b is the 3. And we know that 4 over 3, or a over b, is going to give me 4/3, which is about 1 1/3, and that is obviously going to be between 1 and 2. So this is the case of that dimpled lemmason. And if you look at our equation here, this has a positive sine theta, and so this means this is going to point upwards towards that positive y-axis. So you want to kind of predict in advance what your graph should be looking like before you even start plotting any points. So this is going to be pointing up that y-axis, and then it's going to look kind of like that. Now, to figure out the exact points of where this is going to be, we're going to need to make a table of values. And I'm going to just do my theta values and my r values. And if you look at this graph here, the key points are landing on the major axes. So here at 0, pi over 2, pi, and 3 pi over 2. So those are the points that I'm going to plug in for theta to figure out points to plot on my graph. So we'll let theta start at 0, and then we're going to look at pi over 2, we're going to look at pi, and we're going to look at 3 pi over 2. So if I plug in 0 for this theta right here, sine of 0 is still 0, 3 times 0 is still 0, and 4 plus 0 would be 4. So this r value is going to equal to 4. At pi over 2, sine goes to 1, and 3 times 1 would stay 3. 4 plus 3 would be 7. At pi, sine is back to 0 again, so this goes to 0. 3 times that would stay 0, and 4 plus 0 would be 4. And finally, at 3 pi over 2, we have sine is -1, and 3 times -1 would be -3. 4 plus a -3 goes down to 1. So these are going to be the 4 points that we're going to plot. So if we start at 0, 4, remember 0 is your angle. An angle of 0 degrees would be along this positive x-axis, and I want to go out to 4 and put a dot. Then at pi over 2, which is 90 degrees up the y-axis, I want to go to 7, which would be right about here. And then at pi, which would be over here on the negative x-axis, I want to go out to 4. And then at 3 pi over 2, I want to go to 1, which would be right about here. And then connecting the dots here in this dimpled lemmason kind of a shape, we're just going to have almost this heart shape that's pointing upwards towards that y-axis. And my graphing skills here aren't very great, so use your imagination, but it's going to have kind of that lemmason shape. Now, just to kind of show you how we can do this on our graphing calculator, let's type that equation into our r equals, so 4 plus 3 sine theta. I'm going to check my window here, and we've got the theta going from 0 to 2 pi, so you can just leave these theta settings alone. And then I changed my x's to go from -3 to 3. I have that in my calculator right now. I think I'm going to need to adjust that because we know that those r values went all the way up to 7 on the y-axis and 4 on the x-axis. So let's adjust these and make this go from, say, -5 to 5 for the x's. And we'll just go I'll stay with -3 for the y and go up to 10 for the y max. And let's hit graph. And there's that cardioid shape. Okay? Excuse me, that lemmason shape. All right, so now what we're going to do next, in our next example, is graph r equals 3 cosine 2 theta. So again, you want to refer to your sheet of all the different types of graphs that you could get. And this has the shape of one of our rose curves. And the n here is this 2 that's in front of the theta. So in this case, we know we are dealing with a rose curve because this is looking like an a cosine n theta. The n here is the 2. And because it's even, that means we're actually going to have twice as many petals. So we're going to predict that we're going to have 4 petals. And the fact that this is a cosine means that the very first petal is going to lie on the positive x-axis. So we can kind of predict in advance that the first petal will be on that positive x-axis. The length of that petal is this coefficient 3 right here. So this is going to go out a distance of 3. And since we're going to have 4 petals and they're going to be equally spaced, then the other 4 are going to lie along those other major axes. So that's kind of the shape that we're predicting. So now to get that graph, let's go ahead and make a table of some values. So I'm going to do some thetas and find the corresponding r's. And since these are all hitting on these major axes again, I'm going to go ahead and plug in these 4 major quadrant angles for my thetas. So I'm going to use 0, pi over 2, pi, and 3 pi over 2 again. So if I plug in 0, cosine of 0 is 1. 3 times 1 would be 3. If I plug in pi over 2, remember we need to do 2 times that, and 2 times pi over 2 becomes pi. Cosine of pi is -1, and -1 times 3 is -3. If I plug in pi, that becomes 2 times pi, or 2 pi, which cosine of that is 1, and 3 times 1 stays 3. And then if I plug in 3 pi over 2 and I multiply that by this 2, the 2's cancel, giving me 3 pi. Cosine of 3 pi is the same as cosine of pi, or -1, and so this goes back to -3. So now when I plot these points here, we're going to start along 0, the angle 0 is that positive x-axis, and I'm going to go out a distance of 3. And then what we're going to do next is go to pi over 2, which would actually be the positive y-axis, but I need to go at a distance of -3, an r of -3, which actually flips me down over to here. And then I go to pi, which is going to be over here, and I'm going to go at a distance of 3. And then 3 pi over 2 would be down here along the the negative y-axis, but because my r is -3, that's going to flip me over and end up plotting me on the positive y-axis. So those are going to be these 4 key points. And now all we have to do is just kind of connect these into a nice petal shape. and there would be our rows. Now, if you wanted to be a little bit more specific and careful and detailed, you could actually find where these intersect. But if you think about it a little bit here, at theta equals to pi over 4, 2 times that, 2 times pi over 4 becomes pi over 2, and that's when cosine goes to 0. So it's along this radial line, pi over 4, and the corresponding one in quadrants 2 and 4, that these petals loop back around to hit 0 in the origin. Okay? All right, let's take a look at our next example. Here we have another equation that's of the form r equals 2 sine theta. There's no n in there. There's no sine of n theta. So this is not going to be another rose curve. It's actually going to be a circle. So if you, again, refer back to your sheet on all of the different graphs that can happen for polar functions, this has the shape of a circle. And the coefficient here, 2, is actually the diameter of that circle. And the fact that this is a sine curve means that this circle is going to be up along the y-axis. So just like that, where this diameter here is 2. And you can certainly plot some points, or you can just go ahead and draw that directly. The nice thing about having those graphs sort of memorized is that it can cut down a lot of the work that you have to do to figure out these graphs if you already know in advance what to expect. So there's my circle. And if we look at example number 17, this is also a circle because it has that same type of formula. In this case, it's r equals a cosine theta. That 2, again, is going to be the diameter of our circle. And the only difference is that this time it's a cosine. So instead of being a circle along the y-axis, it's going to be a circle along the x-axis. So it's just going to look like that. And if we go out to 2 here and draw this, let me straighten out my graph here a little bit. And then we have our circle. Okay? All right, our next example here is a slightly bit more challenging. This has the form r squared equals a squared sine of 2 theta. So this is going to be a lemniscate. And this 4 here is actually our 2 squared. So the a here is going to be 2. And it's a sine, so that means we can predict in advance that this is going to be a lemniscate that is along that diagonal line through pi over 4, right through 45 degrees. And the distance along one of these little petals is going to be that 2, not 4, but the actual a value, not 2 squared, but just 2. So this is going to go out to 2 up to the right and down to the left. Now to get some points here to plot, we aren't quite as lucky because this isn't going to be lying on those major quadrant angles. So we can't just use theta being 0, pi over 2, pi, and 3 pi over 2. We're going to have to be a little bit more detailed and go into some smaller angles as well. So I'm going to make a little chart here of my thetas and my r's. And I'm going to kind of think about this graph, and we can kind of see that it's lying along that diagonal line that would be at an angle of pi over 4. So pi over 4 would be a good angle to look at in determining some points on this equation. And I'm also going to look at those quadrant angles as well. So in my list of angles to plug in, let's start at 0, and then I'm going to go to pi over 4, and then I'm going to go to pi over 2, then I'm going to go to 3 pi over 4, and then I'm going to go to pi, then 5 pi over 4, 3 pi over 2, 7 pi over 4, and then back to 2 pi. So all those quadrant angles as well as all of the pi over 4 angles as well. So let's start with 0. If we plug in 0 for this theta, 2 times 0 stays 0, sine of 0 is 0, 4 times 0 is 0, and when does r squared equal to 0? Well, obviously at 0. Now, if we plug in pi over 4, 2 times pi over 4 becomes pi over 2. And sine of pi over 2 is 1. 4 times 1 is 4. And remember, this is when is r squared equal to 4. Not when is r equal to 4, but r squared. And r squared can equal to 4 at 2 different values, at positive 2 and negative 2. So this is actually going to take on 2 different values at that angle of pi over 4. So we're going to go out to pi over 4 and go out 2 up here, but then if we go out to pi over 4, we're also going to have to flip over and jump and plot negative 2 in this direction as well. Okay, let's see what happens at pi over 2. 2 times pi over 2 would be pi. Sine of pi goes to 0, so this is going to be 0. If we plug in 3 pi over 4, and we multiply that by this 2, that becomes 3 pi over 2. Sine of 3 pi over 2 is negative 1, so this whole right-hand side would become negative 4. Now, unfortunately, r squared can't equal to a negative, so this actually has no value. There aren't any points to plot when we're dealing with 3 pi over 4. What happens at pi? Well, 2 times pi is 2 pi, sine of 2 pi is 0, so again, this right-hand side is going to be 0 again. If we plug in 5 pi over 4, 2 times that becomes 5 pi over 2, and 5 pi over 2 is the same as pi over 2. So the sign of that is going to be 1. 4 times 1 is 4, and r squared equals to 4 at plus and minus 2. If we plug in 3 pi over 2 and multiply that by 2, that becomes 3 pi. Sine of 3 pi is the same as sine of pi, which is 0. 7 pi over 4 times 2 is 7 pi over 2. That's the same as 3 pi over 2, and the sign of that would be negative 1. So this whole right-hand side would become negative 4, and an r squared can't equal to a negative. So this is also not going to exist. And then finally at 2 pi, 2 times that is 4 pi. Sine of 4 pi goes back to 0. So we're going to plot some of these points here. So we're going to start at 0, 0, which would be right here at the origin. And then we're going to go to pi over 4. And let me just kind of sketch in that line here so that we can reference it. There's our pi over 4. So I'm going to go, for the plus 2 case, I'm going to go 2 to the right, which would be right here. And then I'm also needing to plot pi over 4 negative 2. So pi over 4 would be this way, but the negative 2 would flip me over and plot down here. Okay, and then I'm going to go to 0 again at pi over 2, so that's back to this pole in the middle. 3 pi over 4 doesn't exist. Pi 0 is right in the middle at the origin again. 5 pi over 4 would be down here, and I would go to positive 2, which would again be this point right here, and then 5 pi over 4 negative 2 would flip me back over to here. So I'm again hitting these 2 points again. At 3 pi over 2, I'm going to 0. 7 pi over 4, which would be over here, doesn't exist, and 2 pi again is 0. So I'm really bouncing back and forth between these 3 points. And knowing the fact that I'm supposed to be graphing a lemniscate, this is where it's going to help us know how to connect the graph between these 3 points, because we know in advance that this should look like 2 petals along the first and third quadrant. So that's going to help you be able to predict what this is going to look like. So there's what our graph looks like. Now I want to show you how to do this on your calculator, and I'm going to show you how we can kind of animate it a little bit to kind of see exactly what's being plotted. So the first thing we're going to do is clear out our r equals. Now we need to plot this as a function. We need to plot this as r equals, not r squared. So in order to solve our lemniscate for just an r, means we would have to take a square root of both sides. And now when you take a square root of both sides, you actually get the plus case and the minus case. So to properly plot this, we're going to have to plot both the positive and the negative square roots in r1 R1 and R2. So for example, in R1, I'm going to plot the positive square root of 4 sine of 2 theta. Close off your parentheses. And then I'm going to plot in R2 the negative square root case that we would get if we were to take the square root of both sides. Okay, so here's my two equations. And I'm going to adjust my window again. Let's just change these. We know that our radius here is 2, that a value was 2, so I don't need my x's or my y's to be very big. So I'm going to change these back to -3 to 3 for the x's, and I'm going to do -3 to 3 for the y's as well. Now let's just go ahead and graph this first. Okay, so there's kind of our lemniscate. Now what I want to show you, let's go back to our y equals. I want to show you how you can animate this so that you can kind of see what path this graph takes as theta goes from 0 all the way to 2 pi. So what you have to do is you have to arrow to the left. See those little slashes to the left side of our r equals? You want to adjust those, and the way that you adjust is you get your cursor over it so that it's flashing like that, and then you're going to hit enter until you get to this little symbol right here. It looks like a circle with a little line after it. And now I'm going to go down and I'm going to change R2 to have that same look. And this is the animation feature on your calculator. So that's the only thing I'm changing. And now when I hit graph, it's going to show me the path of this graph as theta varies from 0 all the way to 2 pi. So let's see what our graph does. So there's the first time around. Then it goes over to the third quadrant. And then it goes back to that third quadrant, and then it goes back to the first quadrant. So it's actually looping around this lemniscate twice from 0 to 2 pi. Okay? So that's just kind of an interesting feature on your calculator that you can use, that animate command, if you need to kind of be a little bit more visual and see what's happening on your calculator and how these points are actually going on your curve. All right. Let's finish up our last two examples. This next one is just r equals to 2. So it's kind of a bare bones type of equation. But remember, this is polar form. So since there's no theta showing up in this equation at all, that means that theta can be anything. There's no restriction on what theta has to do. So if theta can be anything, what's r doing? Well, in this case, r is always equal to 2. So what kind of graph is going to allow us to let theta be anything? So we can sweep around all these angles, but no matter where we sweep, the r value always has to be 2. Well, that can only happen if we sweep around all these angles, but we stay on a radius of 2. And so that means our graph here is just a circle with a radius of 2. But it's a circle that's centered at the origin here, as opposed to the circles we did earlier that were shifted over to the right to be on the x-axis or shifted up to be along the y-axis. Now just a note here, remember from earlier that our r value is equal to the square root of x squared plus y squared. So if you think about this, we can take that and we can substitute that in right here, and we'll convert this polar equation into its Cartesian form. So if we take x squared plus y squared under a square root and we substitute that in for r, then this equation becomes this Cartesian form. And if you square both sides, you can see why we're getting the graph that we're getting, because we're just getting x squared plus y squared equals to 4. And we know that that's a circle where the center is at the origin and the radius is equal to 2, the square root of this constant on the right-hand side. So that's just kind of an algebraic proof of why our graph should look like this circle. Okay, The last example here is kind of the opposite of what we just did. This time there's only a theta showing up and there's no r. So that means that there's no restriction on r, and that means that r can be anything, any radius that you want. But there is a restriction on theta. Theta is always going to be pi over 3. So that's 60 degrees. So let's think about what this graph is going to have to look like. We know that theta equaling pi over 3 would be up here. So if we're letting r be anything, if we have any positive r's, like r being 1 or 2 or 3 or 4, it would just be these points along this kind of array going up like that. But what if r is negative? Theta still needs to be pi over 3, but if theta is pi over 3 and your r is negative, that's actually going to flip you down over here. So these would be all the points when your r is negative. And if you connect all these points together, what shape is this going to be? Well, it's just going to be a line. So when your theta is a fixed constant, a fixed angle, and in this case this angle was pi over 3, and your r doesn't show up at all in your equation, then you're just going to end up with the equation of a line. Okay, so memorize that sheet of graphs of your special polar functions and be real familiar with those so that when you look at an equation you can kind of know in advance what to expect your graph to look like. And then you can always plot some points, some thetas and some r's, to kind of verify where those points should be on your graph. But it's always good to know in advance what to expect. Alright, that concludes our video lecture on polar coordinates. Good luck!